the Lush products, especially when you get to the bathroom and end up lathering myself in it, but it might not just be me. So tonight we have a great lineup. We have our first speaker is actually from Lush, Zach, digging deep into the compiler. That's going to be a fun journey. Alex is then up talking about strings and dictionaries. And finally we have Roberto talking about practical fuzzing. So yeah, a wide range of different topics. Hopefully a really good evening. But first off, I will hand over to Rob from Lush just to do an introduction to health and safety, who Lush are and what they're doing, and also talk a bit about Go. So without further ado, Rob.
Hello everyone, welcome back. Before I forget, I forgot last time, there's a little treat for the speakers as a thank you for chipping in and doing their bit. So don't forget to collect those after you've done your talks. Go at Lush, I wanted to call it 2.0, but we're not there yet. So Go at Lush 1.13.5. The mundane stuff, oh no, I had little GIFs. I had little dancing gophers. Okay, anyway, mundane stuff. I ran it through a thesaurus so it'd be a bit more interesting. So fire egress is the entrance that you came through. Comestibles, if you haven't already eaten, are there. The comfort station is there. If during a talk, if you could use the disabled one in the entrance, that'd be really good. And the plunder, the bath bombs, are just out there. So grab a bath bomb on your way out. We've got 3 different types for you to choose from. We've had a year spent learning at Lush. We've either visited or spoken at a number of conferences and meetups. KubeCon, React, Nordic.js, Google Next, San Fran, London, Star West, which is a QA conference, TNW, Escape Conference in New York, Swift Toronto, iOS Dev UK, Big Data London, and of course Prometheus Go, is it Docsmouth or Muth? Docsmouth. It sounds, you wouldn't go to Portsmouth, would you, or Bournemouth? And CockroachDB. So we've been busy in the back end. These are just a couple of the services we've been working on. So we've got a service for booking, which Zach has written, he's with us today, which handles all of the back end of the booking side of things for spas and hair treatments and everything like that. It's a very extensible system, so you can, any kind of booking that goes through Lush can go through that back end. Products, Z, he's over there, he's written. That's a golden source for all of our products data for Lush, and eventually sundries, so everything that is a product. Stock, I wrote February last year, but we're going to revive that, is a real-time stock management system that allows you to, when you've got a basket, it takes stock out, so customers never over-order stock. Region management, which is all to do with payments and jurisdictions of products. Payments, as you can probably imagine, and a media service. So what's new? The last time I spoke here, everything was REST. Service-to-service communication was REST. Since then, we've been a bit smarter about how we do it. It's gRPC. I think everyone's probably doing protobuf communication between services. It makes a lot more sense. We're not there yet, but it's an ongoing activity. GraphQL from the back end to the front end, again, makes a lot of sense for us. And we've further integrated with CockroachDB. So currently it's within a single region, but we're developing it in such a way that we can span out globally using geo-partitioning, which gives us a lot of flexibility around compliance issues. We're using asymmetric key management for JWT tokens, which is really big. It allows us to be really quick. If there are any security concerns, we can roll keys super quick, which we couldn't do before. And we've created a little search engine for products using trigrams in Redis, which I think is really cool. A couple of open source projects. They're very specific to Lush, but I would urge, if you're curious, have a look. They can all be forked and tailored to fit your needs. One is a core package, which is everything to do with what makes a microservice at Lush, gets you off the ground really quickly. That's not particularly specific to Lush, so I urge you to give it a go, see what you think. Core Mage being a Go version of a Rake version of Make. We use that for our pipelines, the targets that allow us to configure our infrastructure with code, get you from nothing to something in production very, very quickly. Core SQL, anything to do with databases, as you can imagine, ISO 3166, 3-digit codes, I think, at the moment for localization. Core Redis, everything to do with Redis communication and JWT, JWT library. This is really old. We've done more stuff in Lens, but we've moved everything from Core ML to TensorFlow. which allows us to run both on our iOS devices as we did before, but also our Kotlin devices on Android, which blows up the whole market, allows us to get downloaded by lots of different people. We've got currently 50,000 downloads, 1 million scans, a lot of me doing my face and seeing what bath bomb might appear as. This morning, I was going to do a demo, but I'll just explain. I was a princess bath bomb today, which I thought was, I just wanted to share. We've created something called Nigel, which I can never remember what it means. I think it's New Image Generator Enabling Lens. And it's essentially a robot that spins around and takes pictures of products from different angles. It's so cool. But that's Lens. There's loads of stuff going on there. I'm going to get off the stage and hand it over to Zach. So I hope you really enjoy it. Thank you so much for coming back, and it's nice to see you all.
Thank you, Rob. Before we move on to the first session of the night, we've actually got one of our recurring sponsors to come and say a few words. So we've got Bud with us tonight. So yeah, please welcome Bud to the stage.
Yeah, sure. I know you all want to get on and you want to travel this journey through the Go compiler, so I'll be a bit brief. Unlike Lush, we don't have the benefit of you all knowing actually what we do though, so I will just kind of cover that off very quickly. So at Bud, like our mission is one of those kind of like heebie-jeebie missions about making money simple for people. What does that actually mean? Now, think Monzo, right? Monzo, they revolutionized a whole bunch of stuff by giving you PFM tools like categorization or how much money you have left to spend in a month, or telling you that you're doing these payments and you're sending them out every month. And that's great, and inside of a Monzo style experience. What Bud is trying to do is essentially we're working with big banks, think sort of your HSBC style size, to try and deliver that experience through those through with them by exposing APIs. Now, obviously, that means sort of great. We're working with one client. So for today, for example, I mentioned HSBC because we just signed a global deal with them, which is sort of access to 40 million consumers through their retail banking across the globe, which is quite awesome. And it kind of helps us achieve that mission of making money simple. But it goes a lot further than PFM. There's a whole bunch of really cool stuff like, everyone pays rent every month, right? But what it sucks is that when you decide to go and get a mortgage or you get a credit card, none of your rent actually contributes towards your credit rating. But actually what we're doing is we're working with HM Treasury to identify your rent, automatically verify who your landlord is by who you're paying it to, and then having that contribute towards your credit rating. So there's a whole load of really cool producty stuff there. If you're more techie and you don't really, well, not that you don't care about the product you're building, you should care about the product you're building. About 3/4 of our services are in Go. We have all kinds of stuff. We have data orchestrators, we have a data storage layer, which kind of manages, so the way that we handle data security is very specific per user. We essentially, all data is encrypted for very specific users. We can't access it offline. We basically have to be given a key by the bank for a specific customer to be able to access that data. So there's loads of stuff on this kind of security side. What else is interesting? Sort of data parsers and manipulators. We interact with banks through open banking. So yeah, there's lots of sort of interesting technical cool stuff, and there's cool stuff if you like actually making a really important part with people's lives easier and simpler. So that's what we do. If you want to hear about recruitment or anything, come chat to me. I'm not going to keep you any longer. And yeah, I'll hand over to...
Thank you very much. I find it amazing how Go can affect our lives in so many ways, from shopping all the way to banking and finance. I think it's such an interesting area to be in. Afterwards we're going to go for a nice socialising experience at the Jon Snow. So if you want to hang out later, we're all going to be at the Jon Snow. Come and say hi. Tell us what you think. Feedback's welcome. We want to make the meetup better for everyone. So yeah, it's only around the corner, so if you fancy a quick drink. And so first up tonight we've got Zach, our Lush representative for the evening, taking us a leisurely stroll through the Go compiler. So I'm going to hand over to Zach now.
All set? Okay, can you hear me all right? So my name is Zach, and I want to thank you all for coming and contributing to my anxiety about doing this. Welcome to Lush. When I originally set out to do this, I thought it would be leisurely, but I'm not sure that's going to be the case anymore because, you know, as these things go, they just build and build. So my goal is to get us from here, where the compiler is a sort of black box that happens between main.go and main.exe, or whatever you call your executable file, and get us to here, just to fill in what happens at a really high level. Just as a note, this is a massive piece of software. I just doing a word count on some of the directories, just the compiler, which represents these 3 red blocks, is 500,000 lines. So it's huge. I know a good deal about this one very narrow part of it, which is one of the specific optimizations. And you'll see I've kind of tried to represent my familiarity with this as I move through. So actually putting this together has been a great learning experience for me, and hopefully for you as well. Why I want to do this? So when I first started toying with the Go compiler, it was like swimming in mud because I was completely disoriented and I didn't really know the context. I'm working on this tiny little narrow part, and I didn't have a good feel for what all the moving pieces around me were. So I'd like to provide sort of an orientation for anyone who's interested in the Go compiler or compilers generally, or wants to contribute to a large, complex code base. I would recommend you try fixing a compiler issue. And then in case there are a few of you who don't intrinsically enjoy compilers for whatever reason, I think there's some value in filling in the black box a little bit, having a general idea when you build your code, what exactly is happening. Sorry. A note on terminology. So when I say compiler, I'm sort of abusing it, the term. I'm using it in a very general sense. We often talk about this whole process as the compiler, and I think that's okay. It's what it's doing. We say, I'm compiling this program. When in reality, there is a tool being used that does these 3 phases in red that is the compiler. So when I say the compiler, I'm generally referring to the whole thing, but you'll see I'll reference that. Apologies for the confusion. That seems to be the terminology that everyone uses. Also, when I say the compiler, there is not just one Go compiler, there are many. These 2 here are in the standard library built and maintained by the Go team. And so we know that these 2 will satisfy the Go specification. The one in red is the default compiler. And generally when people say the Go compiler, they mean GC, which is Go compiler. I just listed, there's lots of compilers in the community. I've listed 3 of them that I've just stumbled across here. TinyGo compiles Go in constrained microcontroller environments. Tamago is similar, but for larger, less constrained microcontrollers, and Go LLVM uses parts of the LLVM toolchain instead of some of the Go toolchain. So again, I'm going to try to get us from here to here. I'm just going to stop at each of the phases and give a really brief summary. Hopefully I can stay shallow so I have enough time. A really brief summary of what it is, what the current representation of your Go code is, and then the command that you can use to kind of see that part of the compiler happening to your code. So the first step is orchestration. This is what happens when you run Go build. It actually runs a Go build tool that will, as a whole, take your UTF-8 source code and give you a binary executable if you're compiling an executable. This tool is sometimes referred to as a compiler driver. I've heard people call it the build system or a build pipeline. What this blue box does is it takes in your files, determines all the import dependencies, and builds this action graph, which is a graph determining the order of operations that these need to occur in across dependencies to ensure that you've compiled the things that you need compiled before their dependees. Whatever that's called, sorry. It also maintains a build cache. This was super interesting, and one of the reasons I always go over on time because I want to talk about this. So this was added, I don't know, 1.5, 1.8, 1.10, and maintains a cache of all the build artifacts all the way through this process that can identify whether you've changed that source file and only rebuild that artifact if the source file for it has changed. Otherwise, It just draws from the cache. And this significantly sped up build times. And then I've just listed here the two primary Go tools that build will use is Go tool compile, which is the 3 phases in red, and Go tool link, which if you can't see it, the green one down here is called linking, and the linker does the linking phase. As I mentioned, Go build install will run the blue box, the whole process from end to end, and it'll orchestrate everything for you. If you wanted to do it on your own, you could run Go tool compile on all of your files with these long lists of flags and arguments, and then run Go tool link to link them all. If you'd like to see what those arguments look like, I've elided, you can't see at the bottom here, this is huge, and I took many, many lines out of here. But if you run build with the end flag, it'll essentially show you the action graph. It'll tell you what it would do if it were to build that, all the steps it'll take. If you use -x, it'll build it and show you the steps. And I just highlighted in blue that it's creating some directories. It compiles, this here is the compiler tool for my architecture. It compiles it. Build ID is a part of the caching tool, and then it links it. This is very short because everything was in the build cache. But when you run this, if you run this on one of your programs, you'll see that this runs for lines and lines, and you'll see what I cut off the end of this line. It's like 4 more lines of flags and arguments that I probably couldn't explain to you what they meant if I put them on there. If you're interested in looking at the source for the build tool, this was actually really hard for me to find. When you run Go build, try to trace that back to where it's actually going. But I've done it for you. So this file is actually where the build tool is. You'll see some of the things I mentioned: build ID, action, the action graph, GC for the GC tool chain, GCC Go for the GCC Go tool chain. But this is where it is. So now we move into the first phase. So it maps out the dependencies, and it says, OK, I'm going to start compiling. It compiles one file. We move into translation. This is the step where we take our UTF-8 source code, and we have to turn it into some sort of data structure. Code isn't structured enough for the compiler to do much with it, so we need to structure it. The structure that I think pretty much everyone uses for this is called an abstract syntax tree, which in a cartoonish sense is this here. This is done per file. Each file will be turned into an AST. How this works, this is compiler 101. I'm trying to not talk about what compilers are doing, but it breaks your code up into tokens. The scanner breaks up into tokens and feeds into the parser that looks at them and says, OK, can this token, given the previous tokens, is this a valid token given our rules of grammar? If it doesn't, it gives you an error that this code is not valid. Sorry if you can't see, but I'll say these. And then after it's finished constructing the general structure of the AST, it'll then go through, infer all the types, and do type checking. This is also the point where you get, this is also the point, OK? Nope, no better. OK, I'm going to forget to hold this by my mouth. Where was I? This is the point where you'll get that declared and not used error. During this phase, when it just says declared and not used down here. So I remember to tell you that this is where this comes from. I mentioned that the parser is attempting to see if the tokens satisfy the grammar. If you've looked at the Go, am I getting? Oh, you know these. I have this tool that will show me images without. If you've looked at the Go specification, you'll maybe have noticed these gray boxes with all this funny blue links in it. I had no idea when I first looked what this was. This is the specification of the Go grammar. And the parser will have a function inside it for each one of these rules that it will use to try to turn those tokens into the nodes on the AST, I think. Mike? Is that? That's all. This is just a picture from Wikipedia of an AST, and this was just to present to you, like, the Go AST is more on the order of this than the cartoon I showed you previously. You'll see there's a lot more information at the nodes, and it's obviously bigger. If you'd... If you would like to see the AST for your code, you can use this -w flag. So if you don't know, if you do this gc flags flag to the go build command, it passes those flags through to gc, to the compiler. You could also run go tool compile with the same flag, but this will run go build and pass the flags after gc flags through to the compiler for the compile tool. Don't worry about reading this, that's not the point. Just to show you that you'll see, these are all spaced in by dots to highlight the depth on the tree, and this is a textual representation of the AST of something that I compiled. If you would like to see the source, this one is more aptly named. Most of the code for this is in command compile, internal syntax as in abstract syntax tree. I highlighted a few of the words that I mentioned. You see there's a parser file, a tokens file, a scanner file, and others. Those do contain things that do what I explained earlier. The type checking is not in that same folder. It's over in internal GC. I struggled with whether this should be in this phase or the next one, but I put it here anyway. You can see what this file probably is involved with. Okay, so we now have our type-checked AST. We pass it to the next phase, optimization. So in this phase, the compiler is going to try to take your Go code and make the very best, most efficient version of that behavior that it can. I'm not sure of this, but I get the feeling that this is where a lot of the work in the compiler is happening. Maybe lots and lots of it is pretty much in here. And this is where I'm most familiar, so there's a good chance I'm going to talk way too long. And then, so we passed the AST in. For historical reasons, actually, the AST needs to be transformed into another AST that can then be turned into the SSA. But see how it gets slow? So the AST will be transformed into a generic SSA. This is static single assignment. I'll explain that in a moment. This is another representation in data of your code that is generic to all architectures. After some optimization here, it's going to transform it into an architecture-specific SSA. Same kind of structure, but a little bit lower level and specific to the architecture that you're compiling for. There are a couple optimizations done on the AST, referred to as AST transformations. You can see them here. In the file for these transformations is my favorite type that I think maybe I've ever seen, the hairy visitor. So this guy, he walks to the AST and visits nodes and assesses their hairiness. He carries this budget here, or she, hairy visitor, he carries this budget here, and as he walks the nodes in a function, depending on what operation that node is, he deducts some predetermined value from the budget. And if he goes over budget, he says, no, this function cannot be inlined. If he doesn't go over budget, he says, yes, it can be inlined. And then he continues with the next function. You can see him at work by using the M flag. And this will output the optimization decisions that the compiler has made at that AST transformation stage. This was a tiny little file. You'll see that it's, yes, I can inline this function called f, good function naming, and this variable s does not escape to the heap. On to static single assignment. So this is the intermediate representation that Go and many other compilers now use to represent your code. The reason is that, let me explain what it is first. So a control flow graph is exactly what it sounds like. It's a graph that represents the flow of your program from start to finish. SSA is essentially a control flow graph with data dependencies encoded into it. The next slide. This is just the general form. I'll show you specifically on the next slide what that means. And the reason for this is that it's much more effective and efficient at doing optimizations than AST or even the CFG alone. So I have here a really basic CFG off of Wikipedia. And you'll see we have a branch. And within the branch, this variable y, let's say it was defined much earlier. This variable y is redefined within the branch, and then we want to use it down here. Sorry if you can't see, this just says w equals x minus y. It's not even important. So down here, we want to make some sort of optimization decision for which we need to know something about y, like what its possible range is, or I don't know. It's hard to think of these things when you're standing up here. So you need to know things about y. But because we branched up here, we don't actually know which version of y we might have. And if we want to know that, we essentially need to walk the whole graph just for that variable and determine, like build information about it as we go back up, reaching analysis for every one of these. So what SSA does is it essentially turns every definition of a variable into an immutable variable, its own variable. It's often shown like this, whereas each time the variable is redefined, it gets a little version subscript. But it doesn't really matter. This doesn't have to anymore have to have anything to do with x1 at all because it's its own value. It's a different value. And then there's fancy algorithms that will determine where to put these nodes called a phi node. Apologies if you can't see this, but essentially at a join point in your graph, you have to somehow mark that this could be this version or this version of that value. And there's a pseudo instruction, doesn't actually do anything, called a phi node or phi node. That is a representation of, okay, this value, this version of a value here, could be y1 or y2. And then the key thing, I think, these are pointers, right? So if you're here, if you need information about y1 or y2, it's a pointer, so you have it, and then you can instantly access whatever information you needed, and you can know sort of the relationship, like the values of y join or intersect. I don't know which of those right terms is here. If the ranges will intersect here, and you can determine what the range of the y3 is going forward. Oh, I wasn't supposed to go that long at that part. So these optimizations on the SSA are done using two constructs, I suppose. Passes and rules. Passes are done on an SSA that represents the entire function. These are hand-coded functions that take the SSA data, they do their analysis, and then they mutate the SSA based on whatever decisions they make in their analysis. And then the next pass, and then the next pass, and the next pass. So these are a lot of the optimizations that require the whole context and all that semantic analysis to make decisions. The other one, the rules, are the more repetitive and value-specific optimizations. These aren't simple at all, but they're different. This blew my mind when I found it. So there is literally a Lisp-like programming language defined and used only in the Go compiler to build these rules. This took me a really long time. Everyone was talking about, oh, the rules. So because there may be a rule that's doing something that's very similar to a function you're working on to do by hand. And it really confused me. I did a quick check. So there's a file of generic rules, of these rules that will generate Go functions to operate on generic SSA. That's about 2,300 lines long. That generates 47,000 lines of Go code. And then there's also rules for all of the architectures. All of them together are 16,000 some lines and generate 290,000 lines of Go code. So someone didn't have to write 300,000 lines of code. They wrote 16,000. I mean, not that these 16,000 lines. I'm never going to make 30 minutes. Don't worry about reading this. These are just here to highlight the signature of one of these passes. This is the one I'm familiar with that tries to remove unnecessary bounds checks. So whenever you index into a slice in your code, the compiler early on will have inserted a check to determine whether your index is greater than 0 and less than the length to stop you from accessing outside the bounds of the array. But that can be expensive in some hot path that is constantly checking, constantly indexing into a slice. So this function, prove, takes in func, which is the SSA, and it passes through and tries to determine whether it can remove some of those bounds checks by lopping off chunks of the graph, essentially. That's what they look like. Rules look like this. Again, don't worry about reading this. I know I'm not supposed to put all this text on a slide. But the idea here is you see this is like this Lisp-like S expression language with all these recursive parentheticals and stuff. But this one here is, if you happen to have typed x times 1 in your code, this rule will generate functions that find it and change it just to x. because there's no reason to do that. But someone didn't have to write 8-bit times 8-bit 1 and 16-bit times 16-bit 1 and 32. This, you see, using the ORs and the generator will generate all those for them. And then they start to be a little more complicated. And then even more complicated. This isn't even the most of it. If you're into bit hacks, go look at these rules and you'll see craziness in there. They literally use the word magic all over the place. It's like, these are magic numbers. Go see magic.go to see what they mean. I mean, I like know the syntax a little bit. I have no idea what all the F's are. Okay, don't read this one. Also don't read this one, obviously. So what this is, this is the list of passes, the function version that I showed you. This is the list from the code that will determine what they are and what order they'll run in. Just to give you an idea of the scale, it's something like 50. I didn't count them. If you want to, I forgot to put where this is. So if you're interested, come find me and I can show you right where this is if you want to read about what all these passes are. I just want to highlight this one. This one's called lower. This pass takes in the generic SSA and turns it into the architecture-specific SSA. And then if you're in the front row, you can see that there's a lot more passes after lower, after we've turned it into architecture-specific SSA. So we do lots of architecture-specific optimizations. You can also see all of this. This totally floored me the first time I saw it. Except, and does anyone else know what this colon star does? Talk about undocumented flags. I was doing this for months and months, hand drawing all my SSA, and then someone's like, oh yeah, you can just put colon star and it'll show you the SSA for all the, for the entire function. So these columns in a horizontal direction, starting with my source code, is every one of those passes. The pass will contain for me a nice graph viz representation of the SSA in its graph form, which I suppose is kind of a CFG. And then down below, you'll see each of these blocks that is represented up here, which we can even link through by clicking, has some set of instructions in it. But wait, that's not all. So this is the whole thing, all the way through. Lower, you see all those names. This is the, this is still foggy for me. This is the pseudo assembly that comes out of the back of this part of the compiler. Let's say you want to know why this move Q is in your code. Oh, you're just like, oh, it looks like it's coming from line 28. You click on it, it highlights it. We come all the way back to our source. It's literally linking to the line that's producing that line of code. Oops, sorry. And at every point that code is in the SSA, that line is represented in the SSA, it's highlighted as well. So you can follow every line of every piece of code all the way through every one of those compiler passes. If you, oh man. Yeah, right. Here's where the code for the escape analysis and inlining is. Sorry, I'm going to start going quickly now. Did I really think I was going to explain this? This is where I spend all my free time. This is where the SSA source code is. Look, you can't see it down here. I have a legend that tells you what all these colors mean. But this is where it all is. If you want to see it, get it from the slide. Okay, we come out of the back and we're in this architecture-specific SSA. We now need to turn that into machine code, something that can actually be used. The Go compiler does this via this type called obj.prog. Does anyone know if that's a shorthand for something or if it means anything? Okay. This is, best I can tell, this is essentially Go's assembly instructions. Mike, yeah? Okay, this is Go's assembly instructions. So there's a set of methods that will take our architecture-specific SSA, turn it into architecture-specific, but sort of common to all architecture assembly. And then there's a method that will turn that into the binary for the architecture. Again, you can see this if you'd like. Build with the flags with the -S. What's the S? I don't know why it's an S, but this is those pseudo assembly. Go has a weird assembly thing that I can't quite wrap my head around yet. But you can see it. Here's where some of the files for turning the code from architecture-specific SSA into progs is. You'll see there's directories for every architecture there, if you want to see what instructions it's choosing for what operations on what architecture. More of that here. This is turning those instructions into object files, binary files. So the last step spits out these object files, which are, I'm ahead of time. I'm going to go back. These, an object file or many object files or some packed archive. So an archive is just a bunch of these put into a single file, essentially. Yeah? Need to be turned into some sort of format that can actually be executed. Really, run that command and build this and open this in VS Code. Open one of these and see what it looks like. But I guess that wouldn't tell you, obviously you can't execute it because it looks so crazy. You can't run these. They need to be, depending on the architecture, turned into a particular format that can actually be executed. This is called linking. If you can't see it in the back, sorry. This phase is called linking. It's done by the linker. This is where my familiarity with the specifics of Go's case really plummets. This is just a summary of what I got from reading about the Go linker. So these files are essentially a bunch of symbols. A symbol is either a piece of data or a function. And the linker is going to take all those symbols from all those files and gather them up into the appropriate places in the executable file. And it's going to add some headers and some sections and all this organizational stuff that you can talk to like Mike or someone else about if. It does some more optimizations. There's some dead code elimination in there. There's other types of optimizations. It constructs a lot of debug. Dwarf is a debug format. Interesting, I tried to figure out where this came from, and it sounds like just because ELF already existed, they called the debug format dwarf. It doesn't stand for anything. And then, of course, it spits out, it does all this, and then it puts it in a binary file that the executable can, that the architecture can actually run. I'm seriously ahead of time. You had me rushing. There are actually two cases of linking that can happen with Go. It uses its internal linker, or it uses the system's external linker. You can flag it to do this. In a shallow way, and as much as I know about it, pure Go functions can use the Go linker because they don't need anything from the system. There are some exceptions, some particular system files that Go knows to find and recognize, like things related to the net library on Linux. But if you're using CGO or you need C-related things, you generally have to use the system linker in order to link those files into your executable. So the linker will essentially, in this case, the linker will take all of your Go files and make one archive file, like one big object file, and then it'll use the system's linker to link in whatever it needs from the system into your big Go one. You can also see this. So you build, the O flag just lets me choose what I want to name the output of the build, which is the executable. And this object dump tool will do what it's saying. It'll dump the object. I can, with an S flag, and I can pick the name of my function that I want to see and the file. And you'll see this look. So this is the assembly representation over here of what the binary instructions are that were put in that executable. And you can't see it here, and I won't flip back, but these aren't actually the same as the progs that I had for this same code. So if you were to look at the difference of them, you can start to see that it's not actually the same thing, and Go's doing more, essentially more instruction selection after that instruction selection. The source for the linker is in command link internal, mostly in this file LD. You'll see some of the things I mentioned. Dwarf, ELF is a file format, link. I'm going to read this when I get home. I don't know what that does. I always wonder about these ones too. I see these everywhere, go.go. this is the most interesting thing that I found about the linker in reaching for this. So Austin Clements is a member of the Go compiler and runtime team. And in September, he wrote this design document about where the Go linker is at now and what they'd like to do with the Go linker to improve it. It would be an understatement to say that it's like thorough and in-depth analysis of the linker. So if you were interested in linkers or want to learn, this is where I learned most of what I know about the linker was reading his design document. If you just want to learn, this will be a link on the slide that'll link you to a Google document. The outline of it is here. Good read. So we've come to the end. 90 seconds to go. Wow. This took me 48 minutes in one of my practice. So we started at the beginning with source code in UTF form in a file. We turned it into structured data as AST. We turned that AST, we did some type checking and some inlining and escape analysis here. We turned that into this generic SSA, which is our augmented control flow graph. We did a bunch of optimizations here. We lowered that to an architecture-specific SSA, did a bunch more optimizations. We turned that into these progs, we turned this into assembly. The assembly was then spit out as this object file, this unreadable binary that represents the functions and data in your program. That was linked in potentially with some archive or object files from elsewhere to create a binary executable. These were the orchestration was done. If you remember, the blue box was the Go build tool or the Go install tool that was managing the dependencies and the cache and the ordering of all these operations. Translation, optimization, assembly, and linking. Still undecided if I like my names of the. This is what LLVM calls the phases of their compiler. I stole it. And this is where we started. My hope is that it doesn't really feel like this to you anymore, and at least it's blue. There's some color in it. Very sincerely, if you have any questions about this, I literally really, really enjoy talking about this. Otherwise, I wouldn't be up here doing it. Because I'm doing this because my partner doesn't want to talk to me about this. So I've come here and forced all of you to listen to me. But honestly, I really like talking about this. I meant what I said before. If this is how I got into it. If you're into Go and you're starting to work on your projects and doing stuff at work, and you're like, I want to work on something really big and complex, go to the issue tracker and search for an issue in command compile, and just read a couple of them and start digging. It's just exhilarating, I'm telling you. And the community of people who will respond and review your code are very respectful and very helpful. I didn't know what I was talking about, and I ask silly questions all the time, and I get great answers and great explanations about things. I have 2 seconds. I wanted to do this. So if anyone knows the answer to this question, except Mike, I'll get you an extra bath bomb. So this comp Q here. So this comp Q here is a comparison of a word size, a comparison of a quad. This is one comparison. This comparison here is the entire bounds check from that line. So you remember I said a bounds check needs to determine that the index is greater than 0 and less than the length of the array. Has to be greater than 0 and less than the length of the array. That is being done with one comparison. Can anyone tell me how that's possible? This also blew my mind when I got someone to explain it to me. For bath bomb? Paul?
You've already proved this one or the other.
What do you mean?
You've already proved it's greater than or equal to 0.
No. It is literally comparing both numbers.
It's an unsigned comparison, so if goes below 0, it's a large positive number.
Yes, for the bath bomb. This is an unsigned comparison. If the bit representation of the number as a signed number is larger than the largest signed integer, if it's the bit representation, you see, the bit representation of a signed number less than 0 is above 9 million, whatever the largest signed int number is. That number in Go is the largest allowable length of an array, and also would always anyway be larger than the length of your array. So any number under 0 when the bits are read as an unsigned integer, because of 2's complement, get bumped all the way up to the other side and are huge numbers. So as long as your number is less than the length, it's also greater than 0. And that's all. Thank you very much.
There's actually slightly underplayed there, I think, how you actually got into this. You talked about getting into this if you're interested in complex stuff, but I think it sort of extends beyond that really as far as the Go project is concerned. If anybody's interested in getting involved in the Go project, full stop, can you just talk about a little bit about how you got involved with the Go project? It doesn't matter about the complexity of the compiler, because anyone who's interested in contributing should hear this.
Okay, I wasn't working, and I had been like hobby coding for the longest time. And if there's any of you like that, at some point you're like, okay, writing a bot to book my child's creche for me before all the other moms is only so exciting. That's very true. Don't tell them. So I had been coming to the Go meetups, hoping that it would be talks about compilers. No, this was pre-compiler. And I started asking Paul and what he thought I should do. Should I get a job? Should I just contribute to a large open source product? And he said, hey, why don't you talk to Daniel Marti? He knows really well what kind of issues are out there, and he could point you at something. So I went to Daniel, and I asked him for the hardest thing he could give me that I wouldn't understand. So he gave me a list of 5 issues in the compiler. Well, 4, and the other one was, have you ever tried to look at one of the Go presentations on mobile? It's really bad. That was the other issue, and I didn't want to. So I started reading these issues, and that's why I said it's exhilarating. You know when you start reading something and you just don't want to stop, and you're like pretending to use the bathroom so you can hide out in the toilet and read the. So I took one of these issues and I just started messaging, and like I said, people respond. Very respectful and very smart and very knowledgeable people about Go, and they want you to help, and they bring you in and they ask you, what else? And then I fixed one issue, and then people started tagging me in related issues as they showed up on the GitHub issue tracker. And suddenly it just starts flowing through, and people are sending you issues, and then you start to see issues that you know the guy that does that because you just asked him a question about something related. And everyone has just really been so great. I almost didn't get a job because I was just going to do that all day instead. Honest. I just kind of felt bad putting my daughter in a nursery to sit at home and work on the Go compiler. But for some reason, I guess I feel better about putting her in the nursery to come work on a Lush booking service. It's just more socially acceptable, I think, than the previous one. Was that what you were looking for?
Just that, and it doesn't have to be about the compiler. Because I guess the thing is that the Go project accepts contributions from anybody, whether that's actually working on issues and helping work through issues, to something as complex as working on the compiler. And there isn't any more respect really given to anyone who works on the compiler to the people who actually triage issues and help work through issues as well. So it's really, this is a fantastic presentation about how to contribute to the compiler, but the Go project is open to everybody. It doesn't matter what you want to contribute, there will be something you can contribute. And the key thing is, there are people who will be able to help direct you in the right direction for where you can contribute as well. So just reach out to people like Zach and say, hey, I want to do something, and they can help you think.
Look, no one will say, I was worried someone's going to say, who are you? Who's this guy? What do you know? What do you think? I submitted a bug fix to the compiler, and I kind of thought it was going to be oh, how do you know? They were going to assume it was bad or whatever. So look, I went all in on this and submitted with no history of submitting fixes, and they just carried on as if it was business as usual. And I say that to say to you that if you submit something, people will just carry on as if you were another contributor to Go, because then you are, and it will be no issue, I promise you. Well, I can't promise that. No, literally, that's not something I can.
YouTube will be on there. Yeah, make sure you follow. London Gophers study group. So Beth and I think Zach as well run a study group. So if you want to get involved with that, make sure you follow, go to the Meetup, and yeah, go and learn more about Go. Especially it's great for new people joining the language or more experienced people willing to share their time to help others. So tonight we do have a raffle, JetBrains raffle. The code is handmade. If you go to the gophers.london/raffle, type in follow us on Twitter, put in the handmade, and you'll be entered into a raffle to win a JetBrains license. And yeah, we're going to roll on to Alex. So if we can get you mic'd up and switch you in.
Cool. Hello.
Hello.
Oh. Okay, hey, hello. My name is Alexander Petrov. Here's my contacts if you want to chat with me. And yeah, it might be difficult to notice, but I'm not a native speaker. So please don't judge me for my English. I'll try to do my best. And yeah, today we're going to talk about approximate string search in a dictionary. We briefly consider some techniques, and we'll have some practical part with Go, and where I'm going to show how Go helps here with this topic. And about myself, I talked already about this. All right. So I like Go because of simplicity and type system, and I have more than 4 years experience with Go, and let's move. Okay, so here's the list that Google provides us of misspelling Britney Spears. So I want to hear numbers. How many variations do you think there are?
40,000.
No. All right. So it is 593. So there's the link. You can visit if you want. I don't know why, but anyway, you can look at all of them. But you can say, Alex, I don't have Britney Spears on my website. Yeah. Why should I do this? Yeah. And now I'm going to show you the real example. Here's a Google flight page where I'm trying to find tickets to St. Petersburg, but unfortunately Google doesn't want to help me here. So yeah, after complete and fuzzy string support can dramatically increase user experience, improve user experience. And today I'm going to show you how exactly we can implement this feature. So let's try to do this. First of all, we need to take a look at the techniques. So there's a Liebenstein. Sometimes people call it like an edit distance metric. It's simple, it's accurate, and it's line. It means that it doesn't need to know about the dictionary in advance. But there is some restrictions, and it's performance restrictions. We can't use this method for large dictionaries. So another famous technique is signature hashing. It is fast, but it is offline. It means that we should know about the dictionary in advance, and it's probabilistic. And the last one, ngram method. It is fast, it is also offline, and it's a little bit complicated. And today I'm going to talk about this method, and we will try to implement it using Go. Cool. So in order to start with ngram method, I would like to talk about search engines, especially about the key data structure. It's called inverted index. So it works pretty simple. Here we have two documents with ID 101 and text I like Go. And another document 312, I like pizza. So the purpose of this inverted index is to map the term, the search term, to the list of documents where each document contains this term. For example, if we take a look at like, yeah, so there's a document number 101 and 312 contains this word, so it's quite simple. The list of documents we are going to call posting list, and the keys are terms. So cool. Now let's talk about ngram. Here's I provide two examples of ngrams for the word gopher. So 2gram is going to look like this. We just create a window of size 2 and just move this window one by one. And it's all. So let's try to combine all these two things that I mentioned before. Here we have a dictionary. So the left number here represents ID. And there is a inverted index for this dictionary. And in order to find the candidates for our search, what we should do, for example, we have a query, yeah, search query field. We split it into 2grams, and then take posting list from inverted index for ngram ph, and here is for hi and il. So we have these three posting lists, and we try to merge them. As a result, we have candidates with IDs 1, 5, and 6. Okay, cool. Now let's try to code. Let's take a look at the main function. Here's a dictionary that I mentioned before. And it's just a simple scanning from the input, from the std in. And let's take a look at the implementation. So here we have a document ID. It's unsigned integer 32. Here's a term. It's a string for our case. Posting list is the list of documents IDs. And inverted index here is just a map. And here we have two functions. Build index does pretty simple task. We have a loop here for each item in a dictionary, and we split each item into ngrams and trying to build inverted index, so simple. And here our search. We walk through the terms, fetch the posting list, and we use here set to have a candidates list. Let's take a look how it works. Yeah, cool. So I have special paper here. Okay, so let's try to type ph. Do you see? Oh no. You don't see it? I'm sorry. Do you know how to make it? K? Clear? Oh, cool. Thank you. So let's try ph. So cool. Here we have a candidates Gopher, PHP, and philosophy. But when we'll try to type fill, we hear that we see here that philosophy is not at the first position, and we want to sort the list by relevance. And here's the number, enhancement number 1. This is going to help us. So here we have 3 posting lists, and we want to merge them. And while merging process, we can calculate the number of occurrences of each document here. Let's take a look. For example, the document with number 6 has overlap count 3. Yeah, and the other documents have overlap count 1. And when we will, so here we have a pair, yeah, that consists of document ID and overlap count, and we want to sort them by overlap count and return as a candidate list. So let's try to look at how it works, how we can implement it using Go. So main file without changes. So we have a merger file. Here I use some trick to represent pair that consists of document ID and overlap count. And this is why I like Go, because of the amazing type system. Here I store overlap count in the first 32 bits and the document ID in the last 32 bits in an unsigned integer 64. And why I like Go, because I can simply add methods to this type to return position and to return overlap count here. And for merger this, as a merge operation, we use here approach for the merge sort, when we want to merge this sorted list of IDs. And you can ask me, Alex, why do you need to do this, all this stuff? We can use struct with 2 fields. But here the trick is that we're trying to that we store this overlap count at the first 32 bits, and we increment the number of occurrences while merge, and we can just simply use standard comparison operator to compare these merged lists. So let's take a look how it works. So here we just merge this list, this postings list, and use just sort. Cool. This is why I like Go. Okay, let's take a look how it's going to work. Okay. So cool. Philosophy. Oh, I'm sorry. We sorted by overlap count, and you see that philosophy at the first place. It's cool. We can try another one example. Gopher. Cool. But here we have some problem. For example, PH. We see that philosophy now at the first position. But it seems to me that PHP is much better here, yeah? Because we're missing only one letter. So let's try to improve our code, but let's consider our n-grams as the mathematical object set. So here I split philosophy into n-grams, and I remove all duplicated n-grams here, 2 grams here, and London. So cool. And our job is to take a look at the common n-gram between these 2 sets. I tried to put it here. Yeah, it's LO. And it is intersection between these two sets. And now we can use additional helper for our relevance sorting. It is set similarity matrix here. So we have Jaccard coefficient. Yeah, I'm sorry, it is math. And it is okay if you don't understand, because I don't understand either. But anyway, let's try. Here we have our intersection. Cardinality, yeah, it's just overlap count. We already know how to calculate it. But here we have a union. And it's quite difficult to calculate it. But math is going to help us. We'll try to use exclusive principle. And all we have to know here is the cardinality of set 1 and the cardinality of set 2. This is just size of n-grams. Here is the example how it works. So Jaccard similarity between this philosophy and London is 0.09. Okay, cool. Let's take a look. Okay, main without changes. Now we have measure without changes. Again, yeah, I forgot to mention that why I like Go again, because of benchmarks. It's amazing package, and here we can have a proof that yeah, our approach with this pair implementation works good. We don't have any performance issues. And let's take a look at the metric implementation. So it's simple. And at the search, we have now search candidates. And here again, why I like Go, because I can just simply add some methods and we can use this type for our sort package, yeah, using our sort package. So cool, let's take a look how it works in index. Cool, here we just add search candidate to our resulted list, calculate Jaccard distance, and sort, and it's all. Cool. Let's try. I forgot. So here we can type pH, and we see that PHP in the first position by Jaccard similarity, yeah. Gopher at the second, and philosophy at the third, and it works cool. But yeah, we have some problem. For example, here we need to perform some normalization for our data set, and this will be enhancement number 2. It's not number 2. All right. So yeah, in order to implement this cardinality, to get know the cardinality for each document that I showed you just now, yeah, we need to group our dictionary by number of n-grams here. And for example, here we have a list of items with 2 n-grams, and on the other side, a list of items with 5 n-grams, and we just build 2 different inverted indexes, and it's all. So I'm sorry. So yeah, here we should, to perform some normalization, so we use lowercase, and we wrap our Gopher, yeah, use an anchor here, to emphasize, to create 2 additional n-grams to emphasize the start and the end of the query. And now we can look at our result. Cool. Works. Amazing. And yeah, as I promised, we should implement example with Google flight page. So what we have here, so we have here the list of cities with airports. It's 16,000 cities, and I a little bit modified our code here. Again, I'm going to show why go, because it is because of simplicity to convert our sortable type to type of heap element. Here, yeah, we just add push and pop functions, and I a little bit changed the semantic of function search because we don't want to know all these candidates. We just want to know top K candidates here, and yeah, here I use heap for building top K items efficiently. And let's take a look how it works. I'm sorry. Go here. Yeah. So, Moscow. Cool. And it works pretty fast. You can see that it's already production-ready solution. I'm kidding, but anyway, I think it's production-ready. So, cool. So, of course, there's a lot of improvements we can do. We can store our inverted index on disk. So, this approach uses a lot of libraries like Lucene, Sphinx, and other search engines. As you might remember, the posting list is just a list of IDs of integers. Yeah, we can use different compression techniques like variable encoding, delta encoding, and so on. And for a merge operation between posting list, we could use the special algorithms for this. And instead of implementing posting list by ourselves, we can use bitmaps, for example, roaring bitmaps, amazing library. And of course, we can use concurrency to perform all these operations using Go. And maybe some phonetic inverted index, because sometimes we just need to work with names, and for example, for Britney Spears, this approach is perfect. Some resources if you want. Thank you.
Wow, that's a great talk. Great. Right, okay. Anybody who has a job to take over? You got this?
Yeah, so this is a very simple case of use of a weight group, and the problem is not in the weight group, of course. So we are creating a weight group and a done channel. We're never going to write to it, and we add one to the weight group as we should before spawning the goroutine, so this is fine. Then we spawn a goroutine that calls the close function. And then we just call done, and we wait for it. So this part is correct. Let's go to the close function. The close function does a select over the channel that we never write to, and it has a default case. So since we never write to this, this will only be selected, this case will only be selected when the channel is closed. So what happens is that if the channel is closed, we do nothing. If the channel is not closed, we close it. So at a glance, that might seem correct. But there is a problem here, is that the select makes the decision and then calls close. This is not an atomic sequence of instructions. So the select, if the two goroutines arrive in an unfortunate condition, they will both call the select together, and they will both see the channel as not closed yet. So they will both select on the default case and try to close it. And if you close a channel twice, good slide. Actually, I think this doesn't compile because break is a keyword. But anyways, what happens, suspense, I spoiled it, you might see a panic. I've seen this in a pop quiz by David Cheney. He asked, how do you close a channel in a generic way? Well, you shouldn't. That's the point. And there is, I think, no good way to close a channel if you might be on the receiving side of the channel. Closing is a send operation because you send the poison pill over the channel. You should not do that from the reading side of that channel. Okay, that said, I'm going to go through my talk. How much time do we have? 30 minutes max. Yeah, okay, I don't need that much. So that's a link to the slides. I'm going to link it again at the end of the presentation. A little bit of introduction. I work for Google in the security team. I work on web security, and today I'm not going to talk about it. I already bothered you enough last time that I was on this meetup. I'm going to talk about fuzzing. Fuzzing has this long definition. You actually don't need to read through all of that, but the general idea is that you test your program without knowing what your program does. You just throw random data at it, and every time you find out something new, and I'll discuss what new means, you just keep the input and you say, okay, this program accepts this input, let's move on. Why fuzzing? Can everybody read these slides? Okay, good enough. Half of the room replied yes. So humans are terrible at finding edge cases because when you write your code, you write your tests. You write your tests, right? You should write your tests. And you have your code in your mind. So you're following some kind of rules that are not said and are not in the code, but you expect some kind of input to respect some kind of rules. You work under assumptions. Those assumptions are not in the heads of your users, but most importantly, they're not in the heads of your attackers. This is always something that you have to think about. And one more reason to random testing or fuzzing, which are slightly different, is that they're proven to be effective. And one thing that really bothers me is that people think that fuzzing is just an advanced, complicated tool for hackers to use, which to me sounds really weird because I've always seen fuzzing as just another way of testing. So when people tells me, do you do integration testing or unit testing or fuzz testing, for me they're on the same plane, but apparently it's not for everyone. And I have to break you some news. If you don't fuzz, your attackers will. So this is weird to me when people say, yeah, think if someone ever said, yeah, you know, unit testing is just for hackers. Why would you do that? Just, eh. To support fuzzing, you should write fuzzable code. Fuzzable code is usually easy to unit test, and if you write code that is hard to unit test, there should always be a way to execute just your code. If you try to fuzz too much, you're going to incur into some problems, and if setting up your fuzzing environment, like your test environment, takes too long, your fuzzing is going to be ineffective. Think about a web server. You don't want to spin up the entire HTTP server to just send some random text, see, oh, this is not a valid HTTP request, let's spin it, let's shut it down. That is going to take ages. You just want to take, for example, the request parser and throw the text at it. You don't bring up sockets, you don't do syscalls, you just run the data through your code. And your code should be stateless. If you're fuzzing stuff that depends on the state, you'll get some crashes. You will always get crashes. And you will not be able to reproduce them. So you will know you have a bug, but you don't know where. I don't know if you like that feeling. I personally don't. But I know, it depends on what you like in your life. I like to sleep. And here we see the first difference about random testing and fuzzing. Fuzzing uses coverage information. GoFuzz, which is the tool that I'm going to talk about, but now the Go compiler has some tweaks to use other fuzzers, rewrites your code. Every time there is a branch, like an if or a for loop, it adds a little bit of code to say, I got here. And it feeds random data to your program, and let's say it says, okay, I covered 17 branches. And then it feeds more random data, and it says, oh, I covered 20 branches. This new input that I found is somewhat related to the code I'm testing. Keep in mind that fuzzing is black box. So it keeps that piece of data into a folder called corpus, and is going to run over it and modify that new found string to explore more your code. So this is going to explore in a smart way all your code. And if it finds some constants in your code, like strings, it's going to try those out. Because it says, okay, if you're using a constant here, why? And also, why is this a special value for you? So if you take, for example, a JSON parser, and you instrument it with fuzzing, you're going to see a lot of braces in the input, because that's one of the tokens it accepts. And if you fuzz HTTP, after a while in the corpus directory, you will see some stuff containing, for example, get in the body, because why not? I mean, it's a valid token. Fuzzing doesn't know what it's fuzzing for. One very important thing is that fuzzing tries to suppress duplicates. If I find that your library has a problem, for example, it doesn't parse long strings, and I feed it a gigabyte of data, and then I feed 2 gigabytes of data, I don't want those crashes to be duplicated because it just makes it harder to debug. And GoFuzz has some smart ways to deduplicate crashes. Most fuzzers do, and sometimes they fail, so you get tens of thousands of crashes per second, and your computer blows up. And, well, yeah. That said, let's get to the practical part, which is the good part, not too much about theory. So you want to pre-check your input. The fuzz function that you're going to implement accepts a byte slice. That's it, full stop. If you know that your program will never accept a byte slice that is longer than 5 bytes, just straight away reject anything that is longer. That is just going to tell the fuzzer, be faster and just don't feed me useless data. And this is important. When you call your target, the input that you feed to your target needs to be a direct derivation from the input that the fuzzer gave you. So if the fuzzer gives you a byte of value 10, maybe you want to feed 100 to your function, and we'll see how to transform the input later. But if you feed it 10, it should always be 100. There is no random derivation. This should never happen, or again, you will not be able to reproduce your bugs. You need to inspect the return value of your function. I mean, you can fuzz at random, just throw data at a parser, and if it panics, you found a bug. Good. Nice. But maybe it just never panics, but it gives you random data in output, or broken data. You don't just throw random input in your function, you should validate some invariants. And then in GoFuzz is one of the few use cases in which I'm allowed to panic as much as I want, which is nice. So every time something unexpected happens, you should panic. That's what tells GoFuzz something wrong happened. And if you don't panic, you have to return an integer, which is one of these three values. This is how it looks. You have to implement one function, takes a byte of slice, returns an integer. You might want to transform that byte slice. It's fine, you don't have to. And then you call fuzzTarget, which is your function, the one that you don't trust, or, well, if I wrote it, I usually don't trust it. But in the general case, any function that you don't trust. And then if something unexpected happens, you panic. If you think this input is relevant, you return 1. For example, if your parser returns a value and an error, and you got an error, who cares? Your parser just doesn't accept that input. But if your parser didn't return an error and returned valid data, just return 1. Instruct GoFuzz and tell it, this input is important. You discovered something new. Otherwise, if it is something completely useless and you want to tell GoFuzz, never give me this again, you can return -1. I never use this, and I think you shouldn't either. But if you find a good use for it, go ahead and tell me. Comments are opened on this slide. Don't deny of service me, please. And then, if it's not interesting or not too uninteresting, return 0. To run this, you can't use the default Go tool. As I said, you need to instrument your sources, rewrite the sources, so you use an external tool, and you run just a couple of commands. And now I'm going to demonstrate how to do this. This is the wrong file. This is my function. So I decided to write a codec, because codecs are easy. This codec takes a string and returns an integer. If it can't parse it as an integer, it returns 0. It's a safe default. I mean, 0 is nice, it's all round good. And then I write a serializing function, which is write, that takes an integer and returns a string. I mean, this is an easy thing to implement, right? I mean, how could you possibly get that wrong, right? So I wrote unit testing for this. I considered several cases, like 42, which is important. A string just returns 0. A negative number, I thought about this. A negative number returns a negative number, 0 returns 0, and a floating point, that's not really a valid integer, isn't it? So I just return 0. Good. Run the test pass, my code is correct. This is usually where I stop. And think where everyone stops, and this is not nice. Because let's say that I take this fuzz function and I just call my functions. So I read the number, I just treat the input slice as a string. If the number is 0, it's probably random data I don't care about, so I just return 0. I don't care. This is input I don't care about. And then I write the number again, and I compare the two strings. Ideally, if I read 17 and I write 17, they should be the same string, right? So, I'm going to build these. I'm in the wrong directory. So I'm going to build this. You need to use the special GoFuzz build command, and then I'm going to run GoFuzz. This is going to spin up my CPU, and it found a crash. You see, this is saying crashes 1. That crash is probably this panic. So let's take a look at the output files. When you run GoFuzz, it's going to create 3 directories: corpus, crashes, and suppressions. Corpus is going to contain some data that it fed. These are the hashes of that data that it used to discover more code, as I was saying. But let's take a look at the crash. 08. So if it starts with 0, I'm going to serialize it at 8, because, of course, it starts with 0. So this is one crash. I let it run for how long? A few seconds. And it already found a crash. There are 3 more bugs in this code that I found by running it for 10 minutes. For example, if it is too long, it will overflow. If it is minus and then a 0, it will also not serialize that 0. There are several bugs. It's like 7 lines of code. That proves 2 things. Fuzzing is effective and found stuff that you wouldn't expect, and I'm very bad at unit testing. Now, checking invariance doesn't stop at serializing, deserializing back a value. You could also check, for example, if you get an error, the other value should be nil. You don't want to return 2 valid values. Don't do that. Unless you specifically document it, or you're implementing IO writer or IO reader, don't do that. You could check the numbers didn't overflow. That is also a possibility. There is also the possibility of using a reference implementation. We'll see this later. If your package has a state, you could save the state before fuzzing, fuzz, and check that the state hasn't changed. If you expect your function to be pure, the state shouldn't change. And also that there were cleanups. For example, if your program creates temporary file, check there are no more temporary files after your function is done executing. Inspecting a crash it gives you 3 files, GoFuzz, every time it finds a crash. One is the mere input that you can feed your function to reproduce it. One is the quoted input in a Go quoted way. You can just copy it, paste it in your sources, and it's going to be valid. Sometimes you get invalid UTF as input and makes your function crash. It's almost always the case, so it's good to have the quoted thing. And then the output of your program with the panic and the stack trace. This makes it way easy to understand. Question for the public. So, for the audience, what do you think is the quoted thing for? What's very useful and infinitely valuable about the quoted part? Yeah, so every time you find a bug with GoFuzz, take that string and put it in your unit tests. This is very important because if you made a mistake, probably the next person that changes your code is going to make the same. I mean, you know your code better than them, supposedly. Sometimes GoFuzz starts finding too many crashes. If that happens, stop it. It doesn't make sense. If you have too many crashes, you can't manually go through them. You should change your strings or your stack traces or clean your stack traces before you panic, because that is going to be impossible to debug. And also, while GoFuzz runs, it gives you a coverage value. If the coverage goes beyond 5,000, some hashes are going to start colliding and it's going to lose of efficiency. So you might lose visibility on some bugs. So if you get to that value, you might want to change the function you're fuzzing to a smaller one or to one that doesn't depend on that many things, because otherwise you just don't get valuable output. If you get out of memory, crop your input or just write your code better. Try not to get that, because that panics every time if it goes out of memory. It's probably going to be a denial of service on your server, and in any case, you should limit your inputs in your function, especially if they accept untrusted input. This is what I was talking about. Every time you find a crash with GoFuzz, even if it doesn't make sense for you, put it in your unit test. So you're sure that you're not going to make that mistake again, or someone else that touches your code. This is interesting because I found this in a public guidance on what to fuzz. Code that accepts complex inputs, those are usually parsers. If you think that JSON is not complex, we'll see an example in a bit. I mean, integers have proven to be pretty complex, so that is going to be fun. And also, not just stuff that accepts random or complex inputs, but also stuff that goes through complex states. If you have a big state machine, even if it accepts a small, supposedly simple input, you might want to test these with fuzzing. Untrusted inputs. I work in security, as I said, and this is fun because every time I see someone taking something from a database and passing it through functions, I'm always like, did you sanitize this? but it comes from an internal database. Who writes to that? Do you have any idea who writes to that database? And so this is usually most of the input that you should test, not just because you find vulnerabilities with it, but also just bugs. And third-party code. If you have third-party code, and you probably do, you shouldn't trust it. So just fuzz it. Not because people are untrustworthy. If I put a vector in it, you won't find it with fuzzing, but just maybe because the package is not reliable. So let's take a look at it. I'm going to talk about HJSON, human JSON, because we needed another JSON for humans, because JSON were made by aliens. I'm really annoyed by the amount of JSON parsers that are out there. What I'm going to do here, I'm going to create a value, and marshal data into it, the data that I got from the fuzzer, marshal it back. If I can't marshal it, but I just unmarshaled it, that's wrong. I mean, I read it, why can't I write it? I mean, I'm dyslexic, but my code is not. So, and then I'm going to take another value, and marshal it again, and I'm going to compare those values. So you give me A, I marshal it back, and I expect the two representations to be identical. In this case, I'm not using reflect.deepEqual, but fuzz.deepEqual is a simpler form on a smaller package. This is what I was talking about. If you import reflect, you're going to import a lot of branches, and it's going to take ages to compile. So the GoFuzz corpus fuzz package provides utilities to make fuzzing easier for you. In this case, I ran this fuzzer for about 5 seconds, and I found 2 panics. Now, you're going to see all my history. Beautiful. Now, there shouldn't be more bugs because I already reported them and people fixed them. So, comic relief. Okay, so interesting. So they fixed some and they introduced another. Beautiful. So going back to the fuzzing bit, I'm going to report this later. To write this fuzzer, I just took fuzz function from the corpus package that fuzzes the JSON, standard JSON package, and I simplified it. After all, HJSON is a subset of JSON, kind of intersected set of JSON. So I took the code, I copied the corpus, and I let it run. And it found 2 crashes that have been fixed. The corpus, you don't have to overdo it. You can pre-populate that directory. So for example, if you're fuzzing JPEG, it's going to be useful to put a JPEG in that directory because JPEG is a quite complex format, so you can help the fuzzer out. Don't put 12 gigabytes of data in there because it needs to read it. And it can figure out most of the stuff. After fuzzing the HTTP package for 10 minutes, I found perfectly written HTTP2 requests for it. So it's pretty good. I don't know if you've ever seen an HTTP2 handshake, but it's... So, fuzzing stuff is not a parser because so far they were just serialization and deserialization. A colleague of mine was bored because DNS requests took too long and they were unencrypted. So if you do a DNS request, it's going to go in the clear to your ISP, which is able to decode it, which is bad. And also it's going to be slow because most of the time you're going to hop through several DNSs. So he said, is it really that hard to write a DNS proxy? Spoiler, it is. And at one point we hit the problem, we need to cache. Most caches are good for general purpose stuff, not DNS. In the DNS case, you're going to resolve a set of domains over time, every day, and they're very likely to be requested again. But in some days, you're going to request one domain for the first time, you're going to request it like hundreds of times a day. Like because you're looking for a house for the first time in months or stuff like that. So I wrote a custom cache. said decision. And it was so complicated that I didn't trust my unit test, so I decided to fuzz it. But GoFuzz gives you a byte slice. So what I did was create a translate function, which is this one, that takes a slice of bytes and says, okay, if it is too long, too many operation, it's just a cache. I don't care, just discard it. If it is too short, I mean, it's a cache, so I need to like at least do a put and a get to see what happens. So reject it again. And then I decode stuff. So I decided that keys would be 4 characters and values would be 4 characters. And a byte would give me either a get or a put operation. I'm too short. And this is what I used to translate. And the fuzz function does what is called a differential fuzzing approach. Differential fuzzing says, let's take an implementation of your code that is maybe slower or just dumber and compare it with your actual implementation. Like when you optimize your code, you want to keep the old version, the new version, fuzz them together, and if there is any difference, you didn't really optimize, you just break it. So for these I use the map, because a cache is after all a glorified map. And I threw the same get and put request at both implementations, my cache and the map. If something was in the map and was not in my cache, and my cache was not full, that wasn't due to eviction, that meant my cache did something wrong. And so on. So I assumed the Go map implementation was correct. That wasn't true for the HTTP package, so be careful on what you differentiate on. And then I just used it. I used the cache and the map, and I decided to assert a lot. If you see, this die is just a decorator for a panic, and I do it a lot. Any assertion that fails makes me panic. And I found a bug that required 12 sequential operations to make my cache misbehave. I would never have found that with unit testing. Seriously. Maybe even with use, I wouldn't have found it because it requires some get and put and then another get that would refresh the value and then another put of another value, and I really didn't remember. I just put a string, it worked. One thing that is important, if you have a translation function, like this one, you should really write a small program that repros your crash, that takes your input from the corpus and translates it to human-readable things. Because otherwise you're going to see a blob that doesn't really make sense. You want a program to decode it for you and give you in a human-readable format. This is only necessary if you have a translate function. There are some experiments to make fuzzing better, like FZGo tries to accept structured data. Like you, instead of accepting a byte of slice, you say, I accept this struct, fill it with random data. So if it has an int, puts an int. If it has a string, puts a string. It's experimental, but it works pretty well. So it also has an experiment to automatically generate fuzz targets for you to use. That works not as good, but it's still worth a try. Now, how long does it take to fuzz? Forever, literally. After fuzzing OpenSSL for 1.5 years, I'll let you decide if it is 5 months or 6, they found a bug, and they were fuzzing on pretty beefy machines. These might seem like discouraging, but to be fair, the most bugs that they found through fuzzing were found in the first 5 minutes. So you should at least start fuzzing. And if you don't want to fuzz on your machine, you might use cloud services that I'm going to talk about. Chrome supports fuzzing. Just to give an example on what is being fuzzed nowadays. But they didn't update their tests when they added the last element. They added the portal element, they forgot to change the fuzz target. So some hackers did that for them. Good of them. And they won 8K by just reporting to memory corruption vulnerabilities. So as you update your unit test, when you change your code, update your fuzz targets. Because if you add functionality, it should be fuzzed too. Also, portal element, bad idea on so many levels. If you don't want to fuzz your machine and you have an open source project, Google offers machines for you. Google just gives you some CPUs to fuzz your open source project, and if you find bugs, it will report them to you and sometimes give you detailed information on how to debug it. If you use Go, this is a direct link to the documentation on how to do this with Go. So at this point, I would like to ask something, which is, why are you not fuzzing? If you ever an answer for this, if you're already fuzzing, good of you. If you're not fuzzing, I would like to know your answers. And for anything else, this is my Twitter, these are the slides, and if you want fuzzing to become part of the Go command, please upvote the issue. Thank you.
Awesome. Questions? You could take some questions?
Yes. Questions or answers?
Yeah. Or someone could fuzz in constantly for the next 5 minutes?
You can feed me random data. Let's see how I reply.
Hi. That ticket, will that make fuzzing work with modules as well? Because at the moment, GoFuzz.
So it didn't used to work, but it now does. So I tried with very simple programs, and it works. There was one of the latest PRs that were accepted that enables fuzzing on modules, and it actually came from the author of FZGo. So it kind of supports modules, because once it recreated a separate Go path for you and rewrote the sources there, it didn't work with modules, and now it uses the module information to create that Go path. So it's kind of a hybrid approach. I don't know where it fails. It should work for most cases.
When do you fuzz?
So the question is, when do you fuzz?
Do you do it CI or do you do it?
So not on your CI. You don't fuzz on your CI because otherwise you're going to use it too much. You should use a separate infrastructure for fuzzing. But when do you fuzz? Always. Especially if Google is paying for it with OSSS fuzz, just let it run. So especially if you have untrusted input fed to very complex functions, just fuzz. Or be better at unit testing than me.
How close does testing quick, that testing package, get?
So I get that question a lot. Testing quick is random testing. So it doesn't do coverage. It's going to feed random data, and sometimes it's going to find crashes, but it doesn't know about coverage. So for example, if you test the HTTP package with quick, you're not going to find anything. If you test the HTTP package with fuzz, you're going to discover new HTTP methods you didn't know about. Number for all will amaze you. And sorry. So quick is a very simple form of fuzzing without instrumentation and without a feedback loop. I think is useful because it makes you write fuzz targets, sort of, but is not as good. It's not as useful as actual fuzzing. Do we have any other question or answer?
No.
Okay.
Thank you very much. Can you use your laptop to switch back? Ah, fantastic. Pretty good. So that's gophers.london/raffle, and then the code is handmade. The bit we've done. Yeah, just another big thank you to all our recurring sponsors, Vistas, Utility Warehouse, Bud, who we heard from earlier tonight, and Monzo. Without our recurring sponsors, we wouldn't be able to make this meetup happen each month, as well as our venue sponsors. Yeah, this wouldn't happen without those guys. So what's next? Sainsbury's, back to the big auditorium in Sainsbury's, January 22nd. We then Deliveroo, February 19th. These I think might even be up on meetup.com already, and they should be opening, automated opening probably 3 to 4 weeks beforehand. And then in March, dates to be decided, but I think we have a venue secured and we're just waiting for the final confirmations on that. And finally, thank you very much to Lush. Speakers, make sure you grab your swag that they have provided. It's very nice. And free Go stuff on the way out. make sure you take it all, because I don't think Paul wants to take it home with him. And Paul has one more thing he's going to heckle at me. Oh yeah. Oh yeah, forget about the bath bombs, there's none out there. I might just take them all home. Alright, thank you very much. We're going to head to the pub around the corner, so have a good evening. Thank you very much, everyone.